Welcome to MEI Mechanics. We're on the topic of mechanics basic principles, and this is video 1.2, modelling. Now, modelling is a word that you hear quite a lot in maths and in mechanics in particular. And really all this video is just to give a little flavour of what it's all about. We're not going to be doing any sort of detailed calculations, just a little bit of a discussion about modelling and what it really means. So to start off with, we're actually going to look at an example that's not really a mechanics problem. It's just a sort of typical maths problem where I suppose you maybe even without thinking are doing some modelling and making what are called modelling assumptions. So here's a question. If it takes 2 workers 2 days to dig a hole that's 2 meters deep, how long will it take 8 workers to dig a hole that's 4 meters deep? Now, seems like a question that can be tackled with some basic maths, but in order to do that, it is going to be necessary to make some assumptions. Okay, so if you do the basic maths in the way that you'd almost naturally do in terms of the assumptions that you make, then you'd get an answer of 1 day. But why is that modelling? What are we doing here? Maybe even without thinking. So why don't you have a little think yourself about what assumptions you've made if you agree that the answer is 1 day. Because really that question only makes sense, it can only be tackled if we do make assumptions. So the sort of things that in that case we might be assuming are, well, if you've got 8 workers, so you're increasing the number of workers, can they all be in that hole digging at the same time? We need to assume that they can in order to get that answer. Are they going to slow down or speed up even if as the hole gets deeper? It may make sense in reality that if the hole's getting deeper it might become more difficult to get the earth out and so on. Are all 8 workers the same? Are they all as fast? We need to assume that if that's going to work. And again, similar to the first point, as you go down, is the material consistent or do things change? Because in real life, that's what things are like. So we often have to make assumptions if we're going to do any sort of simple mathematics to answer questions, and you need to be aware of that. And when you're getting results from calculations that you've done, you need to make sure that you're aware of the limitations of those results given the assumptions that you've made. So on to some mechanical situations then. So for example, you see this sort of problem a lot in mechanics if you're thinking about objects which are falling towards the earth, like an apple falling out of a tree, for example, the famous situation, the famous story that's told about Isaac Newton. Then, well, all sorts of assumptions that we might make, but in terms of the earth itself and gravity, the assumption is going to be that the gravity is the same strength at the top of the tree as it is on the ground. Now that would really only happen if the earth was an infinite flat plane. In fact, as I'm sure you're aware, as you go higher up, the gravity does get slightly weaker. But it's really only once you're out into space that effect becomes noticeable. So we'll make the modelling assumption almost always when we're dealing with problems like that the effectively the Earth is flat. Other things might be air resistance. We'll often assume that there is no air resistance, and sometimes that's a fair assumption, sometimes it's really not a fair assumption, and that's a judgment that you really need to be making when you're using mechanics. Alright, what about the orbit of a satellite then? What might we assume about the Earth in that case? Now, I don't know how much you know about the idea of orbits and free fall, but you can see this picture here. You've got an imagined sort of exaggerated mountain here, which is going right out into space, way above the atmosphere, where air resistance is going to be a problem. And if something is launched, then it will fall towards the Earth. But if it's launched fast enough, then it actually doesn't get any closer to the Earth. It's just it's like it's constantly falling. And that's one way of thinking about what's happening when something is in orbit. Now, things in orbit stay in one plane, so um, we might assume a lot of symmetry about the shape of the planet, but also we're not going to have to think about a third dimension. So really, we'd just be thinking of the Earth as being a circle here, which really it's not, of course. Um, and even if we were doing something that required us to think in three dimensions, so perhaps if we're modelling the weather, we might still make the assumption that the Earth is a sphere. Alright, and if you know much about astronomy and so on, what you may be aware of already is that planets um, generally are not perfectly spherical by any means, and that's not just because of the roughness of the surface and the mountains. The fact that the Earth is spinning on an axis actually means that it bulges out more around the equator and pinches in between the poles. But often a sphere would be a good model for a planet like the Earth. Okay, here's another example, something literally more down to earth. Imagine that we've got a hole which we're claiming is to be 1,500 feet deep. You'll notice we've deviated slightly from the usual units, but that's not necessarily a problem, and it doesn't really affect this question. So the question is, suppose we think that this hole might be 1,500 feet deep. How could we what could we do? What sort of things might we be able to do to test that out? So have a think about this yourself. Imagine there's a few rules. Imagine you're not allowed to climb down it, not allowed to use a long tape measure or anything like that. Okay, nothing, no sort of nothing that would require particularly sophisticated equipment. What might you be able to do in order to work out how deep that hole is? Have a little think about that. And as you're thinking about it, you may decide that you have to make some assumptions, some modelling assumptions. If it's occurred to you then that what you could do is drop something down the hole, so take a stone and drop it, and you could use a little stopwatch or something, time how long it is between when you drop the stone and when you hear it land. And then using some of the mechanics which we'll see as this course goes on, if you know how long it took for something to hit the ground, then you can work backwards from that to work out how far it fell. So that's the idea. But of course, that's going to involve a couple of assumptions. So in this case, what would be assuming for start is that the motion is vertical. Now, if you imagine just dropping a stone in there, if you drop it perfectly from rest, then it might be reasonable to assume that it's vertical. But what if you just sort of chuck it in casually? Then it might be moving, have a sideways motion as well, and that might mean that it then collides with the walls or whatever. So other things might happen if we don't assume that it's vertical motion. The idea that the thing we throw this stone is a particle, that's something we'll talk more about later as well, but essentially if you're assuming something's a particle, is it assuming it's got no size? Okay, and that would be a fair assumption here really. If you've got a very deep hole and a small stone, then the fact that the stone's got some size, that means that perhaps if you're not careful in what you're doing, you might sort of have to add or subtract the width of the stone to get the depth. That's not really going to be an issue here. And importantly, especially when you're talking about a large distance there that for something to drop through, where it's going to be travelling very fast, there's an assumption there about air resistance, and I would suggest that of those three, that's the one that is maybe the least reasonable at this point, but it is an assumption which is often made. And there's something else actually that you may or may not have thought about. I'll just repeat what the idea is here. That we're dropping a stone. We'll time start the stopwatch at the point that we drop the stone. Let's assume we can do that accurately, and then when we hear the stone land, we're going to stop the stopwatch. I think there are a couple of things that need to be borne in mind about that. So maybe you might want to pause the video and have a little think. What other things might we need to consider here? Well, one thing of course is that we're relying on sound here. We're relying on the sound of the rock hitting the bottom of the hole to travel through the air up through the hole and to our ears. Now, if it's 1500 feet, that's about 500 meters. Sound travels at about 340 meters per second, so it's actually going to take over a second for the sound to get to us. So, if we ignore the fact that sound travels at a finite speed, then we're going to be way out with this thing. And the other thing, of course, which is if when we hear the sound, we then stop the stopwatch, but there's a reaction time in our own brains processing the sound and sending a signal to our hand to stop the stopwatch. That might be, say, half a second or so, but it's significant in the context of a problem like this. So some things which maybe aren't as obvious that often need to be thought about if you want to do something accurately. So this is going to lead into this idea of the modelling cycle. It's a somewhat simplified version of how a real working engineer or scientist might go about things, but the principle here is certainly very important to get your head around, which is that we've got a real world problem that we need to define. And that's up to us. So it's up to us what things we want to go out and find out about, and what things we're interested in, what questions we want to find the answer to. In order to then answer that question using mathematics, we need to make a model. Okay, so that's up to us to decide what assumptions we're going to make. Once we've made those assumptions, we've got some maths. If we're good enough at the maths, then we can analyze that model. We can do the calculations, and that will give us some numbers. That will give us some answers in quotes, which we then need to interpret. Okay, in the context of the model and in the context of the real life situation. And then at that point, we need to think about whether we are happy with our results. Now, if, for example, in that example with the hole, if we then came along later with some more sophisticated measuring instruments, for example, like a laser or something like that, and we found that the answer we got was out by quite some way, then we might want to refine our model. So we might decide to try and include air resistance, for example. We might, if we hadn't already, decide that we need to take into account the speed of sound, and so we can then refine our model, try it again, and go around and then and then do the whole process again until we're happy that our model is giving us a good enough description of reality that we can almost imagine that is really is what's going on. Now, certainly within A-level mechanics, there are some assumptions which are made very often indeed, and these will be mentioned within the start of a question, for example, and often expressed in terms of sort of words which may have other meanings in other walks of life and are almost like keywords or code words, which in mechanics have a very particular meaning in terms of the actual mathematics of what we're going to be doing. So for each of these words, I'll pause for a little while, and you might want to just think for yourself what you think that word actually means in the context of mechanics. What is it actually going to, in practice, mean for us in terms of what we do when we do the maths? So, one assumption which is often made is that an object in a problem is described as a particle. Have a little think. What do you think it might mean in practice for us if we're doing this, if we're told that something's a particle? So all that means is that we're going to assume that the object is very small, essentially just a single point. So we're not going to have to worry about having to add or subtract the width of the particle onto any distances that we're dealing with. Another phrase that you'll often see is starts from rest. Just more precisely, what do you think that might mean? What that means is that the initial velocity is 0. So at the point at which the time t is equal to 0, then the velocity v will be equal to 0 as well. That's what I mean by starts and rest. Smooth surfaces. Now that's one which I think is very be very easy to misinterpret or to not really see the significance of, unless you have been doing mechanics for a while and have got a sense of what these things mean. So smooth in the case of mechanics means that there's zero friction. Alright, now that's quite rare in reality for that to be the case, to be honest, have zero friction. If something's sliding on ice, for example, then that's might be close, or something like air hockey might be even better example where there is very, very little friction. But most of the time, if you've got two objects in contact with each other, two surfaces in contact with each other, and you try to slide them relative to each other, there's going to be a frictional force that resists that. And so that makes the maths a little bit more complicated if we do take that into account. But you'll often see this in problems that they'll be described as smooth surfaces. So if you get told that something's a smooth surface, what that really means is we're going to assume that there's no friction. A smooth pulley. Well, we'll see some pictures of pulleys if you're not sure what those things are at this stage. But if we're talking about a pulley being smooth, what that would mean is that there's no resistance within the pulley itself to the motion of the rope around the pulley. And so, as far as the pulley is concerned, it's not getting in the way, it's not slowing anything down. When we're talking about the tension in the string, and again we'll talk about this later on as well, when we talk about the tension in the string, there'll be the same tension on either side of the pulley. And again, often in the context of pulleys, inextensible string, that basically means something that's not like an elastic band where you can easily stretch it. Okay, so you often have problems involving string, and what that means in practice is that if I've got the string going over a pulley, if I move one end of the string by 1 meter, then the other end of the string is going to move by 1 meter as well. Okay, because it connects the objects almost directly. That the movement in one object will have to involve a movement of the other object, and of course that then leads them to always having the same speed, and always having the same acceleration as well. In fact. So that concludes video 1.2. In video 1.3 we're going to be looking at forces, and we'll see in more detail some of these situations where we've got pulleys and tensions in strings in video 1.2.